to Physics in the AM. This is the vectors here, and we are looking at problems 33 and 34 today. And then you're going to work on the other three, 35, 6, 7. The first question, 33, that we're looking up, wasn't really a calculation one, it was a sketch. An ant climbs at a steady speed up the side of an ant hill, which is inclined at 30 degrees from the vertical. Sketch a free body diagram for the ant. (30 degrees from the vertical. First, let's figure that out for your drawing, because if there was a mistake, it was probably that. Typically, it's given from the horizontal. I'm just drawing a dotted line for the vertical. So 30 degrees from that is like this. There's your anthill. If this is 30 degrees here, this is 60. Anyways, so hopefully you have it like that. But an ant climbs at a steady speed up the side of the anthill, which is inclined to the. Sketch a free body diagram for the ant. So I'm going to just put a box here. There's your ant. Weight force, the normal force. Is there any other forces in this scenario that we're told about? It's not sliding, it's a steady speed, so acceleration is 0. Any other forces to put on this diagram? Well, if it's a steady speed, it must be pushing itself up with an acceleration of 0, but that means it's going to be, I'm going to use disappearing ink here. There's going to be a force that's equal and opposite to the component of the weight force that's pulling down, right? Otherwise, it would be sliding. I'll just put that in real ink now. I'm going to just call it FA for applied force for the ant climbing up at a steady speed, equal and opposite to the gravitational pull force, right? Make sense? I think. Was there anything else that people had on their diagram? That's it. Yeah. Climbing at a steady speed up the anthill. You could basically say that's the applied force is the friction between, like I think of us moving, it's the friction of your shoes against the surface of the floor. That's basically taken into account with the force of the applied force of the ant. Yeah. Because they said in the diagram, inclined at 30 degrees from the vertical, which is not, usually you give it from the horizontal. That's the only monkey wrench. Any other questions? No? Okay, well, 34, this one has math in it. Scott and Becker are moving a folding table out of the sunlight. A cup of lemonade with a mass of 0.44 kilograms is on the table. Scott lifts his end of the table before Becker does. As a result, we got an angle of 15 degrees with the horizontal, which is the norm. Find the components of the cup's weight that are parallel and perpendicular with the plane of the table. Okay. 34. I'll reread again, double check. 15 degrees with the horizontal. So we have a cup here. only interested with components of the weight force. But let's consider this. We know that if it's not sliding, there's a bit of a friction force. I'm just putting these in here anyways. And then there's a normal force. That's perfect. 90 degrees to the surface. What we are interested in is FG. Weight force. I'm going to just draw. $144 kilograms. Okay. We've got. I'm going to call this the X and the Y axis. We've got this force. Fx, Fy. And if that's 15 degrees in the small angle, then 90 minus 15 is 75 degrees. Right there. Okay? Now, to figure out Fg, it's mass times gravity, so 0.44 on 9.8. We're taking an absolute value because it's 9.8. Can't do that in my head, so I'm going to go with 0.44 times 9.8. I'm going to go with 4.3. Components then, the x-axis, weight force. The weight force in the x-axis is equal to the hypotenuse, 4.3 newtons. That involves the cosine. And I can see the way I've drawn my diagram, it's going to be negative, so I'm going to insert the negative sign. 4.3 times the cosine. 1. And the y. That's also downward, so I'm going to insert the negative sign. 4.3 sine of 7. And I'll do the calculation real quickly. 4.3 times the sine of 4.2. That answers that problem. Are we good? Hey, that leaves 35, 6, and 7 for you guys to work on. And work away you will. Questions on 35. I might as well go over it with you guys too now that you've had a chance to think about it. Did you get it done? You got 23.7 or something like that? Yeah. 35. Oh, frozen, that's why. Let me see here. So this is the dentist chair, right? Now the diagram we're looking for that angle. And the free body diagram. Person, 50 kilogram person there. So the weight force straight down. Now, we know that there's a normal force. and I think it was given. Yeah, 449. I'm going to assume that we're using an XY axis system with the ramp that's parallel and perpendicular to the ramp. Okay? Now, there is a component of the weight force. It's right there, FG and Y. And then there's also an FGX, and then the applied force from the back of the seat. Why did I put a G there? Just redraw that so that makes some sense. We actually don't need that applied force with the diagrams. So in the y-axis, sum of the forces, mass times acceleration, not falling through the seat, so we're going to say acceleration is 0. I'm going to use the way I often do. I'm going to use that the sign of the y component of the weight force is negative, so I'm going to build that into this. I'm going to say Fn minus the weight force in the y direction. That's what the negative sign means. I've already taken that negative part. So the normal force, which is 449, is equal to the y component of the weight force. Okay. Almost there. I'm going to have to do something, though. First of all, the weight force itself, without worry about whether it's X or Y, is mg. In this case, 50 kilograms. 9.8. Pushing into the other stuff. 490. Now I'm going to draw that over here. It isn't because it isn't on the X or the Y axis. Okay. Now, we're looking for this angle, and we could do it directly, but you might be used to always using the top angle. So I'm going to do it the way we often do it. I'm going to use this angle, and then we can subtract from 90 to find theta. Okay? You could jump straight in and use your trig skills, find theta direct. But I'm going to keep it more like we've done with other problems. Okay? So 449. Which one? 490 is the green, and that's directly straight down to the earth. But 490, the normal force, is perpendicular to the surface of the ramp. Or in this case, the depth. The normal force, right? That was given. Okay, so I'm going to sub in a value of 490 for FG. And then we know that it is with the X angle. That's where we use sign. From here, it's just a little bit of trigonometry and algebra. You can solve for the sine of x, the inverse of the function, find the x angle, then subtract from 90 to find the angle theta that I have labeled in green. It'll come out to be 23.7 with the rounding that I used. I'm going to leave you with that. You should be able to work it from there. It's no longer a physics problem now. It's just an algebra trig problem. 23.7.